Quantum physics has revolutionized the way we look at the world. From the works of Planck and Dirac to the man that is Professor Schrödinger and even Einstein himself, the world of the quantum has given rise to the world we see today. And at the foundation of that, the wave function. Now, Schrödinger was a physicist by day and sported a rich social life by night, but beyond his personal life, he's most famous for his cat and his equation. This equation, dubbed Schrödinger's wave equation, and specifically the time-dependent variation, solves what is called a wave function, which is what we'll explore today. Let's take Schrödinger's cat, and for the sake of argument, we'll call him Garfield. Now, Garfield was looking for some lasagna as Garfield does, and stumbled into a box with a Geiger counter, some radioactive material, and a vial of poison. Now, I'm sure you know the rest. The radioactive material has a 50% chance of emitting a particle and triggering the death contraption. Thus, the wave function of the system gives a 50% likelihood of the cat being dead or alive, and we can show this like so. We use the lowercase Greek symbol psi to represent the wave function. The wave function itself is a mathematical model built on probability that's a reflection of the possible state a given particle can exist in, and the probability that we'll find them in that state when the wave function collapses. The weird arrows and lines are just bracket notation used to represent a quantum system. Now, here's another bizarre thing about quantum mechanics and the wave function. Taking Garfield as an example again, the Copenhagen interpretation of quantum mechanics says that he is both dead and alive at the same time, existing in a plural of states, or even an absence of them, called a superposition. It's only when we measure him that he takes one form or another, and we say the wave function is collapsed and we've observed Garfield in his eigen state. Now back to the wave function, which can show us two main things. The possible states of a particle, most commonly the electron, with these including things like position, velocity and spin, which by the way has nothing to do with whether or not the particle is actually spinning and more to do with the magnetic properties of the particle, and the probabilities of finding that particle in these states when the wave function collapses. Thus, the wave function is not just a number or an equation, but a probabilistic framework we use to understand the quantum. Once again, if we take Garfield as an example and say he's moving in a confined box and plot his wave function against this position, we get a graph that looks like this. If we square this wave function and plot the graph, we get a probability distribution, and by finding the area under the curve at a given point, we find the exact probability of finding Garfield in that spot. Now, as I mentioned earlier, the wave function is heavily linked to Schrödinger and his work, and thus is a pretty fundamental part of quantum mechanics. So now, armed with the knowledge of what a wave function is, go forth, learn all there is to know about the world of the quantum. Your journey awaits.